Objectives 2 and 3 will be dealt with on two separate videos, Part 1 and Part 2, this being Part 1. At the end of this two-part video, I hope that you can determine the formula for an ionic compound formed between two given ions and name an ionic compound given its formula. Chapter 7, Section 1, Monatomic Ions. By gaining or losing electrons, many main group elements form ions with noble gas configurations. For example, group 1 metals lose 1 electron to give 1 plus cations, such as Na+. Group 2 metals lose 2 electrons to give 2 plus cations, such as Mg2+. Ions formed from a single atom are known as monatomic ions. The nonmetals of groups 15, 16, and 17 gain electrons to form anions. For example, in ionic compounds, nitrogen forms the 3- ion N3-. The 3 added electrons plus the 5 outermost electrons in nitrogen atoms give a completed outermost octet. Similarly, group 16 elements, oxygen and sulfur, form 2- anions, and group 17 halogens form 1- anions. Not all main group elements readily form ions, however. Rather than gain or lose electrons, atoms of carbon and silicon form covalent bonds in which they share electrons with other atoms. Other elements tend to form ions that do not have noble gas configurations. For instance, it is difficult for the group 14 metals, tin and lead, to lose 4 electrons to achieve a noble gas configuration. Instead, they tend to lose the 2 electrons in their outer p orbitals, but retain the 2 electrons in their outer s orbitals to form 2 plus cations. Tin and lead can also form molecular compounds in which all 4 valence electrons are involved in covalent bonding. Elements from the D block form 2 plus and 3 plus, or in a few cases, 1 plus or 4 plus cations. Many D block elements form 2 ions of different charges. For example, copper forms 1 plus cations and 2 plus cations. Iron and chromium, on the other hand, each form 2 plus cations as well as 3 plus cations. And vanadium and lead commonly form 2 plus, 3 plus, and 4 plus cations. Naming monatomic ions. Monatomic cations are identified simply by the element's name, as illustrated on page 204 of your text or on the top of the screen now. Naming monatomic anions is slightly more complicated. First, the ending of the element's name is dropped. Then, the ending IDE, pronounced ide, is added to the root name, as is illustrated at the bottom of the screen now or on page 205 of your text. The names and symbols of the common monatomic cations and anions are organized according to their charges in table 7-1 on page 205 of your text or on the screen now. The names of many of the ions in that table include Roman numerals, as is shown on the screen now. Those numerals are part of the stock system of naming chemical ions and elements. You will read more about the stock system and other systems of naming chemicals later in this chapter. As a visual representation, we have the negative monatomic ions on the left and the positive monatomic ions on the right. You'll notice that the positive monatomic ions on the right, the cation simply has the name of the neutral atom. Sodium is the sodium cation. Calcium is the calcium cation. Copper is the copper 2 cation, and iron is the iron 3 cation. Don't worry about these Roman numerals at this moment. Simply know that this is involved in the name of the iron 3 cation. But with these negative monatomic ions, fluorine is not the fluorine anion, it's the fluoride anion. Chlorine becomes chloride. Iodine becomes iodide. Bromine becomes bromide. Binary ionic compounds. Compounds composed of 2 different elements are known as binary compounds. In a binary ionic compound, the total numbers of positive charges and negative charges must be equal. Therefore, the formula for such a compound can be written, and it gives the identities of the compound's ions. For example, magnesium and bromine combine to form the ionic compound magnesium bromide. Magnesium, a group 2 metal, forms Mg2 plus cations. Bromine, which is a halogen, forms the Br minus anion when it combines with a metal. In each formula unit of magnesium bromide, 2 bromide anions are required to balance the 2 plus charge of the magnesium cation. The compound's formula must therefore indicate 1 Mg2 plus cation and 2 Br minus anions. The symbol for the cation, Mg, is written first. Note that the charges of the ions are not included in the formula. This is usually the case when writing formulas for binary ionic compounds. As an aid to determining subscripts in formulas for ionic compounds, the positive and negative charges can be crossed over. Crossing over is a method of balancing the charges between ions in an ionic compound. For example, the formula for the compound formed by aluminum, Al3+, and the oxide ion, O2-, is determined as follows. 1. Write the symbols for the ions side by side. Write the cation first. 2. Cross over the charges by using the absolute value of each ion's charge as the subscript for the other ion. 3. Check the subscripts and divide them by the largest common factor to give the smallest possible whole number ratio of ions. Then write the formula. Multiplying the charge by the subscript shows that the charge on 2 Al3+ cations is equal to the charge on 3 2- anions, which is 6. The largest common factor of the subscripts is 1. The correct formula is therefore written as Al2O3. Naming binary ionic compounds. The nomenclature, or naming system, of binary ionic compounds involves combining the names of the compound's positive and negative ions. The name of the cation is given first, followed by the name of the anion. For most simple ionic compounds, the ratio of the ions is not indicated in the compound's name because it is understood based on the relative charges of the compound's ions. The naming of a simple binary ionic compound is illustrated on the screen using aluminum oxide. So as we take that information that we now have, where the positively charged ion just keeps its same regular name. In these examples, it's silver, calcium, potassium, and then sodium. We don't change the name. It's the negatively charged ion that we drop the last syllable and we add IDE. So silver and fluorine becomes silver fluoride. Calcium and chlorine becomes calcium chloride. Potassium and oxygen becomes potassium oxide. Sodium and bromine become sodium bromide. Also, please notice that whenever there's an opportunity for like charges, should I say like magnitudes, there's just one of each, no problem. But if we have like a calcium, which is a +2, with chlorine that is a -1, we require 2 of the -1s to balance out the +2, or conversely 2 of the +1s to balance out the -2. Again, this was part 1 of part 2 covering objectives 2 and 3. After the next video, I hope that you can determine the formula for an ionic compound given formed between 2 given ions, and name an ionic compound given its formula.